Good morning, everyone. Welcome again, and thank you for taking part in this webinar on the life cycle assessment for bitumen. It will be organized in 3 parts. First, I will present the main assumption and main results related to this new study. Then we will look at the comparative analysis with the previous study and focusing on the global warming potential indicator. And finally, we will talk about the deliverables, about the tools for you as EuroBitume members, and about the next steps. So let's start with the results of the LCA 4.0. And the first question you may have is, why have we carried out this new LCA? 3 reasons for that. First, because in the critical review of the previous study, I mean the life cycle inventory 3.0, 2 main questions or shortcomings were pointed out. The first one related to the choice of the database for raw data, and especially for the crude oil production. And the second one related to the lack of primary data used for the calculations. And in the life cycle assessment area, we know that the critical review is very important as it characterizes the credibility and the quality of the results and of the data. So it was very important to address these issues. The second reason is because basically a life cycle assessment has a limited lifespan. You can see here the history of the publication of EuroBitume related to the life cycle assessment, and the first LCI life cycle inventory was published in 1999. The version 2.0 was published in 2012, and it is still used by some stakeholders, especially in France, for example. And the third version, version 3.0, was published in 2020 and with an update in 2022, which was the version 3.1. So we are now 5 years after the publication of the version 3.0, and so it was important and a good timing to update the LCA and even to revise it, because I will present you the new assumption, so it's more a revision than an update. And the third reason is because we had to improve the credibility of our data. And this slide will explain it. In the technical or scientific literature, you can find various studies or sources for the environmental impact of bitumen. You have an example here of the carbon footprint expressed in kilograms of CO2 equivalent per ton of bitumen, and according to different sources or studies in the world. And what you can see is that the variability is very significant. And this can be explained, I would say, by geographical reasons, because for example, industrial configurations or energy mixes can be different according to where you are in the world. So it can explain such differences for the carbon footprint of bitumen, for example. But what you can see also is, even in Europe, the variability is very important. And the EuroBitume values are used by different stakeholders. For example, the EuroBitume value 2020 with infrastructure is used or is cited in the product category rules of asphalt mixtures in Norway. The the number 2020 is used in the PCR for asphalt mixtures in Germany, and in France, for example, the SEV Eco Comparator refers to the EuroBitume value 2012. But we have also other stakeholders who are using different sources and different values. For example, the EPDs published by the Mineral Product Association in UK last year. And the point is, we are more and more challenged about the relatively low carbon footprint of bitumen published by EuroBitume. So we had to address this issue, and we did it in the framework of the new life cycle assessment 4.0. So this study was carried out last year. It started in May 2024, and it was conducted in the framework of the task force LCA within Eurobitium. The first important stage was the data collection and the data quality checks. Then we obtained the first results in October, the first report in November, and the external review was carried out in December and January, and we are now in the final stage, which is the publication of the reports. But I will come back later on the deliverables and on the final timeline. And as it was mentioned by Shivan, the reports are now published and available. It is important to understand that this study has been conducted with the collaboration of the Sphera company, which is a recognized company in the area of environmental impact assessment, and Sphera has a very good experience in the energy sector. And the external review was carried out by the company Solinan, and especially with its director, Philippe Ossé, who is well recognized at the European scale, and is, for example, involved in the standardization works. So these two companies are recognized, very well recognized in Europe, and it is very important for the credibility of our results. We considered two bitumen categories in the framework of this study. First, an average bitumen representative of straight-run bitumen and air-rectified bitumen, so covered by the standard TN 12591, so mainly for paving applications. And the second category is the oxidized bitumen, so rather for the industrial applications like roofing or waterproofing. We are on the scope cradle to gate, so it means that we included in the scope the crude oil production, the crude oil transport to the refinery, the different refining processes, and finally the bitumen storage at the refinery. In terms of representativeness, we cover the bitumen production of Eurobitium members in EU and UK, and it's based on the data collection from 17 refineries in Europe, so it represents about 75% of the bitumen production of Eurobitium members, which is a very good result, for example, compared to other industrial sectors. And thanks to the primary data provided by 8 Eurobitium members. The study has two main types of content. The first one is what we call the life cycle inventory. So it's typically a data set. So it's a quantification of the different flows of resources and emissions associated with the bitumen production. So the main flows are presented in the full report. You can see the table on the right-hand side of this slide. But for people who want the complete data set, we also provide a kind of big table presenting all the flows of the different resources and emissions. And this data set is available in the ILCD format, which is a neutral and interoperable format, which I would say is supposed to be usable in the different with the different software programs, LCA software programs. We realize now that it's not perfect because this ILCD format has been delivered by the Sphera for Expert software, and it's compatible with most of the software, but not all the software. So we are now working on an additional format which could be usable by all the software programs available on the market. The second type of result is the life cycle impact assessment, LCIA. It's the transformation of the different flows of resources and emissions into impact categories, and we choose to deliver these impact categories in compliance with the standard EN 15804 plus A2, which is the reference standard for the construction products, I mean for environmental declaration. And in this standard, we have 38 indicators. So we provide in the full report these 38 indicators related to the bitumen production, including, of course, the global warming potential over a 100-year period. But not only, we also cover other indicators like acidification, eutrophication, water use, waste, etc. In the rest of my presentation, I will mainly focus on this global warming potential, as it is the most widely used indicator by stakeholders, for example, in public procurement, but also in contracts between stakeholders. But once again, the 38 indicators are available in the report. So this is the result for the global warming potential. On the left part, you have the refined average bitumen. So typically the new reference number for the carbon footprint is 530 kilograms of CO2 equivalent per ton of bitumen. As you can see, the main part of this carbon footprint is related to the crude oil production. It represents about 70% of the carbon footprint of bitumen. And after, you have other important stages, for example, the distillation processes, which represents about 15%. You have the crude oil transport and the bitumen storage. For the oxidized bitumen, we add the oxidation process at the refinery, which of course consumes energy and so has an impact on the carbon footprint of bitumen. So the number for this oxidized bitumen is 616 kilograms of CO2 equivalent per ton of bitumen. In the rest of my presentation, I will mainly focus on the refined bitumen. I mean this new number, 530 kilograms. And if we zoom in, especially on this number, so on the left part of this histogram, you find again this value, 530. But these histograms represent the distribution of the carbon footprint according to the different bitumen production stages, but also according to the different greenhouse gas. So we observe again that this part, I mean the crude oil production, represents the main part of the carbon footprint of bitumen, so around 70%. Then you have the distillation processes, the transport, the crude oil transport, and the bitumen storage. And we have also the distribution of the different greenhouse gas. So in dark blue, you have the carbon footprint related to the CO2 emissions. In light blue, you have the carbon footprint related to the methane emissions. And as you can see, the other greenhouse gas, including the nitrous oxide, are insignificant. So we will focus on the methane and on the CO2 emissions. You can see that the CO2 emissions represent just over half of the carbon footprint of bitumen, and methane emissions around 50%. What is very interesting here is, as you can see on this stage, crude oil production, the main part of the carbon footprint of crude oil is related to methane emissions. And that's typically a new result, I would say, compared to the previous study, but I will come back specifically on this point later in the presentation. This is another example of an indicator which is the eutrophication. I won't comment the results. Just to remind you that in the full report, we can access these 38 indicators with the numbers related to the different production stages of bitumen. So we can move on now to the next point, which is the comparative analysis with the previous study focusing on the global warming potential indicator. On this chart, you see again the new numbers related to the LCA 4.0, so the 530 kilograms for the refined bitumen and 616 for the oxidized bitumen. On the left part, you can see here the numbers, the carbon footprint taken from the life cycle inventory 3.1. And if you remember, we have two different values in this LCA 3.1 corresponding to without and with infrastructure. What we call infrastructure is the construction, the maintenance, and the operation of the different infrastructures used for the bitumen production. For example, the refinery, the pipelines, the ships, the wells, etc. And what we observed in the previous LCI is the impact of infrastructure was significant. But for the stakeholders using our publication, our LCI, it was not easy to choose which of these values to use for their own calculations. So for the new LCA, we decided to deliver only a single value, one for the refined bitumen and one for the oxidized bitumen. However, this issue of the infrastructure impact is addressed in the framework of a sensitivity analysis, which is available in the report. What you can see on this chart is, of course, a very significant increase of the carbon footprint. Compared to the previous studies, this increase is around 145%. So we, of course, have to explain it. And in the next slide, I will do it. And it's important to understand that the main changes in the results are related to a change in the LCA methodology and especially in the LCA assumptions. So in this table, you have the different assumptions for both studies. On the left part, the LCI 3.1, and on the right part, the LCA 4.0, the new study. And typically, the choice of the crude oil database has been changed between both studies. In the previous LCA, we used the IOGP database for the crude oils, for IOGP for International Association of Oil and Gas Producers, which is a database which present data at the level of region or continent. And we used in this previous LCI a 5-year averaging for this crude oil data, I mean from 2015 to 2019. In the new LCA, we are now using the Sphera Managed LCA Content, MLC, database, which is considered as more accurate on 2 points. First, on the averaging, on the geographical averaging, because this Sphera database is based on an averaging by country of origin, which was not the case, I remind you, for the IOGP database, which was based on an averaging per region or continent. So we are more accurate. So the Sphera database is more accurate for this averaging for this geographical averaging. And we know that within a single region, the variability of the carbon intensity of the different crude oils coming from the different countries, the variability is can be very high. So it was important to be more accurate in the framework of the new LCA. And this database is also considered as more accurate in the way of modeling the methane emissions, I mean the ventings, the flaring and fugitives, because it's based on the tool which is called the Global Methane Tracker, published by the International Energy Agency, and which is based on satellite measurements. So it's considered as more accurate as the method used in the IOGP database. The second change is related to the crude oil mix. The crude oil mix was estimated by Eurometrium members with the reference year 2019 in the framework of the previous LCI. In the new study, we are now using primary data coming from the 17 refineries that I mentioned previously. So from these 17 refineries, we collected the crude oil by country of origin, and it was then weighted by the individual refinery bitumen production. So we obtained something which is considered also as more accurate. And we choose also to use a 3-year averaging. So we took into account data from 2021 to 2023. We also changed the allocation method at the refinery. In the previous study, we used what is called the sensible heat method, which is a theoretical calculation to assess the energy used to heat the bitumen from the crude oil temperature to the bitumen temperature. In the new study, we are now using primary data and an allocation method by energy. So once again, based on the primary data from 17 refineries. And for the bitumen storage, it's the same idea. We are now using primary data. And in the previous study, it was more a theoretical approach to estimate the energy consumption for the bitumen storage. And this is an example of the change, of the effect of the change in the crude oil database on the results in this table. So once again, we changed from the the IOGP database was used in the previous LCI, and we are now using the MLC Sphera database, which is based on a new way to take into account or to account for the methane emissions. And in this table, you have an example. It's just an example, but on this example in the US, you have a difference in methane emissions, which is about 6 kilograms of methane per ton of crude oil. And you know that the global warming potential of methane is around 30 times higher than the CO2. So these 6 kilograms represent about 180 kilograms of CO2 equivalent. So of course it has a very significant impact on the results. So if we consider again the impact of changing in crude oil database on the left part. So the first bar on the left is the result taken from the LCA 3.1, and on the right part you have the LCA 4.0. Of course, we observe again that we have a very significant increase of the carbon footprint related to the crude oil production. But what is interesting is that for the CO2 emissions, the results are very close. So the real difference is typically due to the way of accounting for the methane emissions. Sorry, yeah. So we can move on to the next point, which is the effect of the crude oil basket. It was not possible to compare directly this effect of crude oil basket between the new study and the previous one because the calculations were not made with the same assumption and the same databases. So we propose to make to address this issue in the framework of a comparative or a comparative analysis or a sensitivity analysis. So we considered 3 different scenarios. The first one is a baseline scenario, which was used to obtain the main result. I mean, this 530 kilograms of CO2 equivalent. So it's based on the 5-year averaging, but we also considered 2 additional scenarios. The first one is a 5-year averaging, which means that we took into account the evolution of the crude oil mix over the 5 past years. I mean, between 2019 and 2023. So we considered all these evolutions of the crude oil mix. It is presented at the scale of a big region or continent, but of course we have the data, as I mentioned previously, related to the crude oil by country of origin. It's presented in this form, I mean, with this scale of region because of confidentiality reasons. And we also considered a third scenario, which is the last year available, which is the year 2023. What we observe is typically the effect of the crude oil basket or the crude oil mix is significant. You may ask why we didn't choose the last, I mean the year 2023, because it's supposed to be representative of the current situation, and it's a good question, but we decided to use this 3-year averaging, considering that we don't know how this crude oil mix will change in the future, and it may be very different in 1 or 2 years. So it was considered as more appropriate to have this 3-year average to have a certain stability, because we won't change the values and numbers, the reference numbers every year. So it was considered as the best option to present the results. And the last point is the impact of the allocation method at the refinery. I just remember that we changed this allocation method. The sensible heat method was used in the framework of the previous study, and we are now using the energy allocation. Once again, we cannot compare directly this effect between both studies, because once again we didn't use the same database and the same calculations. So once again, we propose to present a sensitivity analysis focused on the allocation at the refinery. So on the left part of this histogram, you have the baseline scenario. So once again, this 530 kilograms obtained with the energy allocation, and on the right part, you have the sensible heat method. So just to remind you that the sensible heat method is a theoretical approach used to assess the energy consumption to heat the bitumen from the crude oil temperature to the bitumen temperature. So basically, we use the heat capacity of the bitumen, and we use the temperature difference between the crude oil and the bitumen. So basically 140 degrees, for example. And we obtain the results that you can see in this table. So on the left part, you have the result with the allocation by energy, and on the right part, the sensible heat method. When you compare the carbon footprint obtained with both approaches, you can see that the difference is not high, maybe between 2 and 3%. So it's 518 compared to 530. So it's not a big difference. However, if you focus only on the distillation process, you can see that in terms of energy consumption, the difference is around 40%. So it is significant at the scale of the distillation process. So once again, we choose the energy allocation because we have primary data, so we had no reason not to use them. But we are not really questioning the sensible heat method. Probably it would need further investigation to better understand why we have such differences on the results, but we could do it later. But anyway, we choose to use this energy allocation at the refinery. Yeah, sorry, I had the animation. So just as a synthesis, we present this waterfall, which is basically the explanation of the difference in CO2 emissions between the previous LCI. So on the left part is 216 kilograms of CO2 equivalent, and the new result 530. And between these both bars, you have the difference between both studies according to the different bitumen production stages. So first, the feedstock supply or the crude oil production, which represents the main difference between both carbon footprints. Then the transport of the crude oil, the distillation processes, which present about 50 kilograms of CO2 equivalent. Then the refinery overhead, and finally the bitumen storage, which presents about 25 kilograms of CO2 equivalent. So finally, what we observe is that the main difference, once again, between both studies is the way to account for methane emissions. So it's a key result for explaining the difference between both studies and both results. Yeah, it's the same synthesis, but with words. So the three major factors influencing the global warming potential indicator increase are the change in the crude oil database and the crude oil mix, which represents around 100% increase of the GWP. Then the modification at the allocation method at the refinery from the sensitivity heat method to the, sensible heat method to the energy allocation. So around 25% increase. And finally, the change in the bitumen storage model at the refinery, which represent a plus 12% increase in the carbon footprint. And if we put the new result in this histogram that I presented in the introduction, you have these new bars, I mean for the average bitumen and for the average oxidized bitumen, and you can see that the new Eurobitumen values are in the average of the other sources presented in this on this histogram. So the last point is deliverables and tools available. So in terms of deliverables, you have probably seen that we published these two important reports on Monday. So we have this blue report, which is Eurobitumen Life Cycle Assessment 4.0 for bitumen, which includes a life cycle inventory. So I remind you of different flows in resources and emissions. We have the life cycle impact assessment, which is a transformation of these flows in impact categories, including the global warming potential indicator. And in this report, we also present the critical review, of course, which is very important for the LCA. In addition to this report, we have the LCI dataset, which is available in the ILCD format. Sorry. And which is more for LCA practitioners who can use this dataset in their own LCA software. We have this green report, which is a summary and comparative analysis with the previous study and focusing on the global warming potential indicator. And we also published a frequently asked question on the Eurogym website, so for the stakeholders, which can, of course, change in the future if we collect additional questions from the clients or from the stakeholders.